Okay, so I'm going to do some more examples now of momentum. We talked about momentum, and the symbol of momentum is Juggy, as Deadpool would call him. Now, I'm an old school Marvel Comics reader. This is one of my kids' toys. Despite what you might think, a lot of these things you're going to see belong to my children. Okay. Once he gets going, nothing can stop him. Okay. Wolverine, can't stop him. Thanos, well, maybe Thanos can stop him. But interestingly, that this is an X-Men character, so he's been in the X-Men movies, but he's really a Marvel Comics character. So they could have fought, now that I guess it's all owned by one company. Interesting. So by the way, a lot of people don't realize I mentioned this. You might not believe me. Well, first of all, Juggernaut premiered in the X-Men, right? And X-Men is a Marvel comic, even though they licensed out the films to another company. So I've got this X-Men omnibus, and there's Juggernaut and Kane Marco, and he was actually Professor Xavier's half-brother. Okay, but amazingly, Professor X is a mutant, born that way. Okay, and I guess when he was a teenager, his powers kicked in, and then he became the strongest mutant. But the Juggernaut found an enchanted emerald. So what are the chances that one family would have one guy who's the most amazing mutant in the world, and another guy who's amazingly lucky enough to find an enchanted emerald? Anyway, so this is old school X-Men. See, Spider-Man should be in there. All kinds of cool stuff. Anyway, speaking of Marvel Comics, obviously everybody now is familiar with Thanos and his craziness. Now, I looked at my kid's toy of Thanos. This is funny. But because they do these like a hand with only 4 fingers, so it looks more cartoony, they only gave him that many stones. So actually, he's only got 5. He should have 6, right? Because like the Infinity Gauntlet has 1, 2, 3, 4, 5, the knuckles, plus the one in the middle, 6. So they actually left one out for that toy. Isn't that hilarious? Okay, but this is the villain people are familiar with. Okay, but that's a pretty good Avengers story. But do you know what the best Avengers story ever was? The best Avengers story? It was not the early ones, the really, really old ones. Okay, even that's when they found Captain America. But it was this one. So I hope they do this someday. I hope they do these movies. 3 cows shot me down. Were they spherical cows? This is the Kree-Skrull War. Man, that was great. And that's actually one that they had Mantis in. This is what Mantis was supposed to look like, but they have her in Guardians of the Galaxy now. But she's very different, totally different. And then they did the Ultimates. In the Ultimates, they actually had Nick Fury. Nick Fury looked just like Samuel Jackson. I can't find a good page with him. There he is. He was supposed to be Samuel Jackson. This is way before the movies. Okay, that's why they cast him. Okay, but guess who the next villain is going to be? Everybody knows Thanos. Everybody knows Thanos, but I don't know this, by the way. I have no inside knowledge whatsoever. I just I used to read the comics all the time, but I think I know who their next villain has to be. Because if you have somebody like this, you can't have like a bank robber as your next villain. So who's it going to be? Who's it going to be? This guy. Do you know who this is? Bum, bum, bum. This is my kid's toy version. Kang. He's one of the only Avengers villains who's anything close to being as powerful as Thanos. Super cool one. I hope they do that. I hope they do that. And by the way, I have no idea whether they do that. Okay? So a Juggernaut was named after a device. And again, here's the closest thing I could find to it. Again, my kids' toys. My kids' toys. Okay. A Juggernaut was an Indian device. It was originally a religious thing, but it would just have so much momentum that people would get in front of it, and their momentum wasn't enough to make a dent, had no effect on it, and it just kept plowing over them. So it would run them over. It's kind of messed up. And then later they adopted it in warfare. So the thing about a Juggernaut has to be something really massive, and it has to be generally on a slope, going downhill. If it's on the upper slope, it's really easy to push something downward. It's a lot harder to move it on a flat surface, and especially not upward, okay? So how does this relate? Marvel Comics to Star Wars, well, I guess this kind of does. And I guess they did have something called a juggernaut. I never realized that in Star Wars. But the way I thought of it as relating is because of this. Give up, Anakin. I have the high ground. And then, of course, we all know, oh, this is a spoiler, huh? Well, you know what happened. Okay. So a juggernaut, I just thought it'd be funny. I thought of a way to relate Marvel Comics and X-Men comics to Star Wars, and it just struck me as being really funny. I don't know whether you think it's funny, but I think it's funny. So he's a good symbol of momentum. Maybe we can stick him over on the side here. Oh, we already did this problem. This was the problem from before. So now I'm going to do the next problem. What's our next problem? Oh, yes. Oh, yes. To perfectly elastic. Believe me, I thought this was funny when I wrote it. Well, let's see. Okay. To perfectly elastic spherical steel cows roll together on a flat frictionless field. So what would that look like? Well, this isn't a field. Here we go. There's a field. Okay. Spherical steel cows. So I don't have any steel cows. This is kind of close. Steel cow rolling on a field. Moo. But, oh yeah, well these aren't steel, but they're iron. Iron is mostly steel. Okay. Ugh. And, oh, there's the big cow. So let's see. Big cow is moving west at 2.5 meters per second. Little cow is moving east at 4.1 meters per second. There's little cow. I tried to make them look like steel. I don't know if that worked. Immediately after they collide, little cow is now moving west, which is that way, at 3.5 meters per second. What is the velocity of big cow now? You could almost say, how now, big cow? People don't realize we used to say that a lot back in the 70s. That was an old saying, so maybe it's funny. Okay. How, it used to be how now, brown cow. Okay, ready? Here we go. Watch. Okay, so notice that this one, after colliding, had a greater velocity. And you can probably expect that to happen under most circumstances, but not necessarily, because what if they were going like that? Okay, there's other combinations, and it does depend on a number of factors. So these are two spherical cows. Maybe I could put their faces on here. Are those their faces? Moo! I hope I remember to do that. Two spherical cows rolling in a field, just like spherical cows do. Now, why am I using spherical cows again? Why is he using spherical cows? I'm using spherical cows because I want you to remember that physics models reality with mathematics, or I like to say mathematics. It models reality, but it's not perfect. It's an approximation. This helps you remember that it's an approximation. Using spherical cows, well, that's obviously an unreality. So that reminds you that this is just an approximation. So take it easy with your answers. Don't go overboard, keeping way too many digits after the decimal. It's an approximation. And there are no spherical cows. And there are no frictionless fields. I guess if you just mowed it, it would have more friction if I put the Lego side up. That would have more friction. Let's see if that actually makes a difference. Doesn't make too much difference because these have a lot of heft. These have a lot of mass and therefore a lot of momentum. Okay, so how are we going to do this one? By the way, why does it say perfectly elastic? Elastic objects are objects that bounce back to the way they were. So when these collide, you don't see the shape changing. Okay, that would be different if I had two wads of clay. I should have brought them. If you smash two wads of clay together, they don't go back to the way they were. They get flattened. These, they'll bounce off each other, they'll keep the same shape, or they'll go, even if you can't tell, there will be deformation, but it will be so small, you won't see it, and they'll go back to their regular size almost instantly, okay? So that's what elastic means. Spherical is like a ball. Cows, you know, okay, Muka, okay? In German, it's Kuh, that's the word for cow, okay? They roll together on a flat, frictionless field, and then these are the masses, okay? 476 kilograms. Moving west at 2.5 meters per second. Those are the right units. Okay, good. Little cow, 303 kilograms, those are the right units, moving east at 4.1 meters per second, those are the right units. So wasn't Mr. Pemble nice to give us all the right units that we need for our equation? And remember that the momentum is conserved, so whatever goes in comes out. When I wrote this, I thought I could put in the system twice, but I thought if I just put it once, it would. I'm not sure if I worded this perfectly. Also, it should say closed system, but then it was getting too wordy. So the total momentum of all objects, I could have put in the system before an interaction, is equal to the total momentum of all objects in the system after the reaction. Because remember, this only works in a closed system. And here, well, we're on Earth, so there is a field force. Gravity is pulling everything toward the Earth. But the normal force, if something is on a table, it's balanced by the normal force. Anything that's on a table, okay? So let's get some of these going. All right, so we're going to be using this one. We want to do the initial momentum is equal to the final momentum. The sum is equal to the sum, right? So what we can do is we could put these together and solve for, let's say, big cow, little cow. And then we have to decide which direction is going to be positive. I'm going to take big cow's direction, because it is the big cow. The direction it's going is positive. So positive is going to be to the left. And in this case, it's west. So let's say that's west, that's positive, east is negative. Boom. Okay? And you can choose whatever you want as long as you make it clear. And I would say in your answers, you should tell me east or west. You should tell me. Remember, the other way to write conservation of momentum is this way, and this is actually how we get the momentum anyway. So it's kind of like always this way, really, but this is just a better way to think about it. You've got 4 things here. You need 3. Do we have 3? Well, we've got enough for these 2 initial conditions for sure. And then immediately after they collide, little cow is now moving. Okay, so then we have enough for the little cow. Let's call that B. Little cow can be B. Oh, but wait a second. Do we have its mass? We have its velocity. Do we have its mass? Oh yeah, it's the same mass. You're not assuming that after things collide, after they collide, their mass isn't any different. It's the same mass, okay? And by the way, this was one I ordered, hoping it would be a good one. It was really cheap, but look how big it is. And the problem is, it's so light, it's so low mass, that if you get it going, see how it shifts itself? Oh, it's actually not doing it now. It shifts itself around. So I messed it up. It kills the momentum. It kills its own momentum just by the way it shifts around. So we're going to start with the momentum of each cow at the beginning. So that is positive, that is negative. West is positive. So I'm going to leave this equation right here, and let's write in the numbers that we know. Okay? So we're going to keep, this cow is going to be, this will be cow A, and this will be cow B. Let's just do it that way. Okay? And we're taking A's perspective. Okay, we're assuming that that's positive. Okay, so what is the mass of cow A? It's the big cow. Okay? So the mass of cow A is right there. So 476 kilograms. Why would I pick that? Is that an important date in history like the other ones? I wonder what happened on that date. Oh yeah, the fall of the Roman Empire. It's interesting how many important dates end in 6. Weird, weird, weird. But fall of the Western Roman Empire, the Eastern Roman Empire lasted for another 500 years, but let's not get into that. Okay, then the velocity of cow A, this one, the initial velocity, is going to be, must be this. So this must be my VAI. Maybe I just want to mark it there just to make sure I'm keeping track of it. Okay? And this will be my MA. Maybe I'll write that there just so I keep track of what I'm doing. Okay? And so it is 2.5 meters per second. Okay, so that's this. And then it's going to be plus the mass of cow B, right? Oh, by the way, we're defining this one, I should put, let me not forget it this time, positive. That's positive. Okay, so the mass of little cow, 303. Oh, that's just a small little cow. Okay, I'm about 100 kilograms, so that's 3 times bigger than me, but it's still small for a cow. Okay, and then the velocity of little cow is east at 4.1 meters per second. So that is 4.1 meters per second, right? But it's negative because we've defined, you could do it this way. You could write this little symbol that shows that your x, this is your x-axis, that's the direction of positive. You have to define that, okay? Or in your answer, you could just say east or west after your number. So it's not just the unit, you probably want to say the direction. Okay, and then that's going to equal, just to save space, what I'm going to put on here for now, I'm just going to put my PAF is the way I wrote it, plus PBF. I'm writing those a little bit like rho. I'm in the habit of writing Greek letter R's, the rho, and it looks a little bit, that's supposed to be a P, not a rho. Okay, row, your boat. So now if we multiply these together, we'll have our momentum. I guess I should move over to the left a little bit. So 476, that's when Odoacer, the German tribes ransacked Rome, the fall of the Western Roman Empire, times 2.5, I can't think of anything interesting about 2.5 right this moment, equals 1190, and then what are my units again? Oh yeah, kilogram meters per second. That's this one. So that is, remember, that is PAI, okay? Plus this one, okay, 303, did something happen in 303? Not that I'm aware of. Okay, times, well, negative 4.1, but I don't put the negative in the calculator. I just remember. Okay, remember, it's going to be negative. Whatever you get is going to be negative. Equals, okay, negative 1242.3 kilograms meters per second. Are you surprised that this number is bigger? Are you surprised that the baby cow has more momentum than the big cow? Are you surprised? Well, why is that? It's going way faster. Now, cows don't typically move very fast. This would be really fast for a cow. Slow down, baby cow. This would be real fast. Okay, so now we know that that equals PAF plus PBF, but maybe now we should split that up, okay? At least one of them, okay? So let's see here. The one we have information about is, okay, so we didn't write it in here, but this is MB for baby cow, and this is VBI. So then this one over here, because we've defined baby cow as B, this would be VBF. So we have VBF. So now if we want to split it up like this, if we want to split these up into what they really mean, okay, so the ones that we don't have, well, we do have the mass of the big cow, MA, right there. We have 476 AD, 476 kilograms, okay? And then what we don't know is its velocity, okay? That's what we need to solve for. And we also have over here the mass of B, which we used before, which is 303 kg. And we do have its velocity, its final velocity. Now that is west. So is that positive or negative? How did we define things? Oh yeah, so we said this way, okay, this would be west, this would be east. So going west is positive. So now that's a positive velocity, right? So I've got to put my positive 3.5 meters per second. Just barely fit it on there. So let's do our number crunching. Let's add these together. Even though one is negative, it's still adding, really. Okay, so addition and subtraction, kind of the same thing, you know? If you have a negative number, just think about it. Okay, so it is easier to type in 1190 minus 1242.3. But remember that this is adding them. We are adding them. It's just that this is a negative number. So I'm going to do it the easiest possible way on my calculator. Let me type it in again to make sure I didn't hit that twice. 90 minus 1242.3 equals, and what I get is negative, the total momentum on this side is negative 52.3 kilogram meters per second. So that's not a lot. Wow. With all this momentum in the beginning, and this is all we got as the net moment, as the overall momentum. That's because if you have momentum going this way and momentum going that way, they kind of cancel out. And sometimes they could completely stop each other, and that would be fine if the initial momentum, if these were both the same numbers, one was positive, one was negative, that would equal 0. And that would mean it would be perfectly fine if they just stopped at the end. Think about it. Okay, so that equals, I can't number crunch this, so I'm going to keep this 476 kilograms times VA final. And then I can multiply these, so let me do it. Okay, 303 kilograms times positive 3.5, so it's going to be a positive number. And what I get is plus 1,060.5 kilogram meters per second. Okay, so now, first of all, we have to do 2 steps to finish this off. First of all, we've got to get rid of that, order of operations. We want to get rid of whatever is added or subtracted to our unknown variable. So we can subtract both sides. Let me just write this in red. We can subtract 1,060.5 kilogram meters per second on this side. And we could subtract, now this is getting tricky, 1,060.5 kilogram meters per second. So here's the thing, this number is already negative. And then we're subtracting a positive number, so we might as well just subtract that number. Okay, but this is already negative, don't forget. So the combination of these two is going to be even more negative than this. It's hard to talk about negative numbers. Even more negative. So if you want to make things easier on yourself, you can think, well, they're both negative, or I'm subtracting this, and this is negative. So why don't we add them and then just put a minus sign? That is what it's going to equal to. Do you see why? It's like adding them, so I'm going to add plus 52.3, and what I get is 1,112.8 kilogram meters per second. Is that right? No, remember? Because I have to remember, oh yeah, don't forget, this is negative, negative. And in this case, negative means to the east. Okay, so the overall momentum was actually to the, oh no, we haven't solved for it yet. We haven't solved for it. So then equals, so then I could say that that equals 476 kilograms times VAF. So all we have to do now is we have to divide by what is attached to our unknown variable. We want to isolate our unknown variable. We want to get it on its own. Get rid of its roommate. That roommate is multiplied on, I'm going to go with this metaphor. We're going to divide it off, 476 kilograms, but you have to do things to both sides of the equation. To be fair, to keep it equals, you got to divide both sides. I'm not an English teacher. Okay, so then obviously when we divide those, the kilograms are going to cancel. And I'll have to write it over, I'm running out of space here. I have to write it over here. I might have to bring in more paper here. Okay, so 1,112.8, 1,112.8, I typed it right, divided by 476 equals not that much. Not that much. It equals, I'll write it over here, in green I think, 2.33. I'm rounding, notice how I'm rounding up that 2 to a 3. Oh yeah, wait, that was negative. A negative divided by a positive is a negative. The kilograms cancel, so it's meters per second. And then this cancels, the unit cancels, equals VAF. Oh, but wait, Mr. Pemble, you said put things in scientific notation. I guess I'll have to do it up here. So yes, this is the answer, but I'm going to put it in scientific notation, and I'm going to indicate whether it is east or west. Okay? So 2.33, well, you might say it's already in that form. So how many times did I need to move the decimal? 0. Don't forget, if you don't have to move the decimal at all, then it's 0. Oh wait, don't forget the negative. You still need the negative, even if it's in scientific notation. And by the way, remember, a negative exponent doesn't make the number negative. This does, though. And then you can't just write this without the units, meters per second. And then that equals, I'm writing this backwards, that's fine, VAF. That's the final velocity of the big cow. That's the big cow, A, okay? A, I can make it red. So there is the best final answer. And that's not that fast, okay? But let's see, how does that compare to how it started, okay? So if the big cow was originally moving at 2.5 meters per second, okay, to the west, well, which way is it moving now? Okay, remember, that was positive. So what would this be, okay? You could indicate, just to be extra clear, we did put the negative, but you could say east. Because remember, west is positive, that means that east must be, this way must be negative. Okay? So you could either say the word east, that would be acceptable, or you could kind of show it with the number sign, but then you would have to show something like this, which directions you've chosen. So that's the way we found out how now, big cow. This is how that big cow is moving now. Sounds like Dr. Seuss. Negative 2.33 times 10 to the 0 meters per second to the east. So in other words, this is what happened. Replay, instant replay, instant replay. Two spherical steel cows on a field. And which one is going faster here? This one was going faster. This one is going faster. Then they bonk, collide. And then we know that this one is now moving backward, not quite as fast as it was moving forward, but still pretty fast. And this one's moving back this way, okay? So that's how you do this kind of problem. You have to consider the momentum going in, and then that's got to be the momentum coming out. Now, by the way, if they both had equal momentum, when they were coming together, they could have just stopped each other like that. And that would be conservation of momentum. Because if you have, let's say, positive momentum and negative momentum, they can, if they're the same magnitude, they can whoosh, add up to 0. That's why you can have two objects starting with not moving, then they push on each other and separate, and you can figure out how much each object is moving. Oh, that's the next one we're doing. That is what we like to call recoil. So you might recoil in fear from this problem. So obviously it's just before Halloween, so we recoil in fear from the vampires and the zombies, right? So this is an appropriate one. I got to change the paper and flip. Let me flip it. There's the next one, the recoil problem. So enough with the spherical cows, okay? Let's be a little more realistic. Okay, so to be more realistic, we're going to use people, but we're still going to be making some approximations. So keep in mind, this is a modeling of reality with mathematics. So what we're going to do is we're going to use an equation that has to do with the conservation of momentum, but the equation might make you recoil in fear, like this cat is. Okay, recoil in fear. Okay, because it's a recoil equation. Recoil can be calculated if the objects begin at rest. So here's an example. Two motionless ice skaters face each other with their palms together. Skater C, I guess we'll identify one skater as skater C, is 90 kilograms. So the M of C equals 90 kg. That rhymes. And then we've got skater D, okay, the lady, and her mass is M of D equals 65 kilograms. Okay, so we got that down so far. The ice is extremely smooth. Okay, I didn't just do that because I'm Italian, part Italian. I did that to emphasize the word extremely. So we're going to assume that that ice is so smooth that we can just ignore friction. It's always good to ignore things. They push apart with a high 10. Well, you know what a high 5 is. So think about it. What's a high 10? Both skaters move backward from their own perspective. So notice, he's moving backward, she's moving backward. They're still facing each other, okay? But from our perspective, one of them is going left, one of them is going right. If skater C is now moving with a velocity of negative 8.0 meters per second, what is the velocity of skater D? So we know one of the velocities, that's it. How are we going to do this equation if we just know one of the velocities? Let's see, that is, what is that one? That is skater C, so that's VCF equals negative 8.0, and I don't have room to write it, I'll just put it over here, meters per second. So how can we do this if we only know one of the velocities? Now this has A and B, but we could have just as easily made these C's and these D's. C's and D's, C's and D's, right? So all we really know is, let's say this one, well you can't do it unless, wait a second, no, we know more than that, don't we? Motionless. What's your velocity? What's your velocity when you're motionless? 0. So what's your momentum when you're motionless? Oh, wait a second, wait a second. If this is 0, let's say the velocity, initial velocity for both of them is 0. 0 times anything is 0 plus 0. This whole side is 0. So it's going to be 0 equals this. 0 on this side equals, you know, MAVAF plus MBVBF. That's the new modified equation. So we can do that. So we do have enough information because we have this whole side, because it collapsed to 0. That's always nice too. Ignoring things is nice. Collapsing things to 0 is even better. So now all we have to do is solve for these numbers. Oh, you know, they've already conveniently rearranged it for us. So we don't even need this. We can use this. This is a rearrangement. I'm trying to be dramatic. A rearrangement of that equation. Now be careful, because there's a negative number here. Okay, so let's see, do we have anything else? We've got the MC, we've got the MD, we've got the VCF, and, well, hers we don't know, but it's going to be VDF equals, that's what we're looking for. That's our unknown variable. So I'll put this over here, and let's put the equation right here, and let's just solve it. Let's do it. It's not that long, really. There's not that much stuff here. Not as many different things we have to do. So let's be very careful. It's a good thing we wrote it like this, because we know what VCF is, so we can just put that number on this side right there. So negative 8.0 meters per second. Don't forget the negative. So what does that mean? Oh, wait a second. If that's negative, then what's positive? If going that way is negative, so let's do a little sketch like we did before. Let's draw our little y-axis, a very short one, and then let's draw like a number line, okay, like this. So if that's negative, then this must be positive. And this is my x-axis. I can't write it on there, but this is my x-axis. So positive, negative. We've defined our terms. The question defined them for us. We didn't get to define this. So it was already told to us. So we best make sure that our answer is positive or negative, right? Now, what do we need here? This is weird. This is weird. We've got these parentheses, and then inside we've got the two masses. But I'm pretty sure that masses can never be negative. I'm pretty sure that doesn't happen. Well, the reason they did that is because they had to put the negative somewhere. They could have stuck it outside the parentheses. It might have gotten missed or ignored. They couldn't really put it here because that's the variable you're solving for. That would be confusing. So they had to put it somewhere, so they put it on the numerator. It doesn't mean that one of the masses is negative. MD, that's not negative, okay? But you put a negative sign in front of it. Negative sign. Negative 65 kilograms. Don't break your mind trying to understand what negative 65 kilograms are. Don't break your mind. Okay, and then MC on the bottom, okay, that's this one. 90 kg, okay? And then what's the other thing? VDF, oh, we don't know that, so we'll just keep that as VDF. Now remember, we are calling them C and D. We could have called them A and B, just to change things up a little. And now positive is that way. Last time positive was this way. Positive is the way you define it. Okay, so now let's do the next step. I'm just going to rewrite negative 8.0 meters per second because that's going to stay the same. And then if I divide, ooh, wait a second. I don't like putting negatives into these calculators. I mean, I could with that little nifty plus minus button. But what? Oh, look, it does -0. What does that mean? Wow. Okay. So I like to just leave that out and think with my head and say, negative divided by positive gives me a what? Negative. So we're going to have a negative number here for sure. 65 divided by 90, well, that's smaller numerator is going to be less than 1. Divided by 90 equals 0.72. Now I might stop there, but wait a second. I'm going to keep one more. That's weird, Mr. Pemble, because usually you like to say round to the hundredths place. But listen, if this were in scientific notation right now, that's where the decimal would be, and I'm keeping 2 digits after that scientific notation decimal. That's a good way to think about where to round. If you round things too much, sometimes you can run into problems, so be careful. Usually I tell you don't forget to round, but then sometimes you can over-round. Oh yeah, what's the unit of this? What's the unit? Is it kilograms squared? Is it kilograms? Oh wait, kilograms divided by kilograms. That's the sound of air. There is no unit. This has no unit. It's a unitless ratio. Uh-oh, danger, danger, Will Robinson. Oh, I don't have that one. Danger, Will Robinson. Okay, so what that means is we have to keep track of what that number is. Unitless ratios can be very confusing to people. Like, for example, if your score in a class is 0.722, you wouldn't like to hear that. You would like someone to say 72%, and you definitely don't want it to be negative, so that's a bad example. We just don't like unitless ratios, so sometimes we dress them up as percentages. We magnify them by 100. Parts per million, we magnify them by 1,000,000. Parts per billion, and we magnify them by 1,000,000,000. But you're just kidding yourself. All of those things are unitless ratios, just dressed up with some fancy little dressing, some fancy little clothes. Percentages, ppm, ppb, that's all, I don't know what to say. I don't want to use bad language, but that's spherical cow excrement, guys. Spherical cow excrement. So those things are whatever. I guess we take solace in our percentages. We take a little bit of solace. So I'm going to put that in parentheses, and we're solving for VDF. So what do I got to do? I'm not an English teacher. What do I got to do to get my unknown variable on its own? Well, I have to divide both sides by its roommate. It wants to get rid of its roommate and live alone. I love this metaphor now. I'm going to use it all the time. If you divide it by that exact same number, including the negative sign. Don't forget, the negative sign is included, and the unit is included. Oh, wait, there is no unit. Psych. Okay, so there is no unit, and then on this side, we divide by it too, because you can't do something to one side of an equation without doing the exact same thing to the other side, or you break the equation. You got to keep it equal, right? So when we do this, let's see. Well, you know what's going to happen over here, right? Let's just cut to the chase. When you divide something by the exact same thing, it becomes 1, disappears. It actually becomes 1, but we usually say it cancels out, but that's becoming 1. When you multiply by 1, it doesn't change anything. And then on this side, let's go. Now, I like to leave out the negative signs when I'm dividing. I just don't want to deal with that. But I know that a negative divided by a negative is going to give me a what? Positive. So I'm sure this is going to be positive. And we're dividing by a number that's about 10 times smaller. So I expect this number to be around 10, 10-ish. So 8 divided by 0.722 equals 11, that's pretty close to 10, 0.08. And that's enough. The next number is 0. So again, I'm getting back to rounding to the hundredths place. What's my unit there? Oh, what cancels here? Oh, nothing cancels because this didn't even have a unit. So it remains the same unit that it was before. That's easy. And then that equals, oh, what's left over here? Oh, is the negative sign still there? No, even that cancels. Number cancels. There is no unit. VDF. Boom. That is the answer. right? Didn't Mr. Pemble say something about putting everything in scientific notation? Oh yeah, Mr. Pemble said to put everything in scientific notation. So let me rewrite this. I'll write V, D, F equals, it's still going to be positive even if it's in scientific notation, but now we're going to move the decimal over. So it's going to be 1.1, and then you know what? This 8 will round the 0 up to 1. So I'm rounding it to the hundredths place in scientific notation, 1.11, and then it's times 10. How many positions did I have to move that decimal? How many places did I just move it? I moved it just once. So 10 to the first. Remember, anything that's in the tens place is going to wind up in scientific notation being 10 to the first power. And then, am I done? No. Don't forget to write your unit. You've got to write your unit or it's completely wrong. Even if you did put it in scientific notation, even if you remembered the positive sign that tells you the direction, it would still be wrong if you didn't put the unit, which is the same exact one. So you just carry it down, meters per second. So if you do that, if you write whether it's positive or negative, put it in scientific notation, write the unit, are very careful with your calculations, then boom, 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 that is your answer. So recoil isn't really that bad because the equation has been sort of knocked down. It's been, they've taken out the sides that were 0, they've compressed it. So that's not too bad. You just got to be very careful, especially with the negative signs. And again, there's no real negative mass, but you need that there to make the answer come out right. The reason that's there, by the way, is because whichever way one of them is going, the other will be going the opposite. So if this one's negative, then this one will be positive. If this one's positive, this one will be negative. So that's an easy way to double check if you got the right answer for your recoil calculation. Check if the one that went in, was negative, then the other one that you're solving for has got to be positive. So that's how I can double check that I'm right. Okay, so that's the end of the example. And now you can probably complete the assignment. Okay, thank you guys. Bye. Bye-bye. These were my kids' toys. By the way, Ian, are these your toys?
What?
Is this your toy? This is yours, right? Did you break this? Ian! I did that on the video. I said Ian. Okay.